let's just continue with the basic execution model. We will discuss this a lot more further as we discuss JavaScript and React for us to understand or keep in touch on how it actually uh, is part of a bigger system. So yes, this is exactly the level of basics you should keep revisiting. And you're asking the right follow-up. Is execution flow different per app or the same per language? How does my React plus TypeScript plus Supabase app actually map to stack or heap to OS to async flow? Let's go deep and connect your real stack end to end. First, are these fundamentals the same across apps? Core answer. The fundamentals are the same. The execution flow, shape changes depending on the app. Think same physics, different architectures built on top. So stack, heap, event loop always exist. But how often or how complex their use varies per app. Your actual stack end to end, let's map your real setup. React front end to browser JS engine v8. Then that browser will commit HTTP requests to your Vercel node.js, which written in TypeScript, and then we'll connect to Supabase. Now we'll trace one real flow. First, React function component front end. So we have function user profile. So as you can see, it is a Pascal case. So it starts with a capital because it's a function. And then we have cons user comma set user equal use state initial value null, then use effect to fetch API slash user. So we use effect because it's a third party API, and then dot then rest.json, then dot then data, and then we have an empty array. So the reason for empty array is because we only need to render it at first render, and then after that it won't re-render again, unlike with undefined or with not putting an array here. And then return div user question mark dot name and then div. So what happens in memory or browser when rendering in call stack? Render user profile, function executes, push to stack. So it will be pushed to stack where the instruction pointer or program counter of the CPU will execute that line by line, and then the variable user stored in memory. Heap important, the user state is stored in heap. So the user state here, so as you can see, we use a use state. So this user is a state, and then set user is the function being applied if the state change. So that user state are stored in heap. So after the CPU collect or execute the one in stack, it will now point to this user state to reference that variable, which is what we do here, cons user. And then variable user, React internally keeps a link structure of hooks. So heap user is initially null. Then use effect async flow. So since that heap is initially null, this use effect that will contact third-party API will put value into it. So fetch function is not executed immediately. It's sent to browser APIs outside JS engine. So the flow, fetch function, browser, handles network. So that fetch are the browser API that handles the network. Then second, JS continuous non-blocking. It will execute other function on the app depending on how your app are structured. So that's related to how complex your application is implemented. Then third, response returns to callback queue. And then fourth, event loop, it pushes to stack to be executed by the CPU. So if it is being pushed to stack, it means it is now on the queue to be executed by program counter of the CPU. Then set user runs, triggers, re-render. Or this set user, where is that? set user function will run and triggers the render. So the set user will only run if it receives that data from outside. So that use effect basically changes when it receives those data, or this set user function is only executed when it receives the data, and that set user triggers the render because it triggers the change of state in new state. HTTP request to backend Vercel. Now request goes to /API/user. Third, Node.js TypeScript backend on Vercel. Example: export default asynchronous function handler parameter rec comma rest inside this cons user equal await get user from db function semicolon. Next line rest.json parameter user semicolon closing. So this default async function, as you can see in the keyword async, it means this state that this function is asynchronous, that accept rec and rest, and then it awaits a get user from db. So if our front end like asynchronous to wait for the backend, our backend asynchronous to wait for the database. So execution in Node.js. So this handler get user from db. Each function equals stock frame. So each function in backend are put into the stock frame, and local variables equals the stock, and the objects is equals to heap. So remember in JavaScript, whenever we create something, it's a variable unless otherwise specified not variable. So that variable was are being put into stock. So function in JavaScript is an object. That's why it's in stock frame, and objects is equal to heap. So function is a little bit different with object because it has a pointer being assigned to it. An object has a pointer as well, but function is different in that in the back end it has a stock frame compared to an object which is heap. Async behavior: await get user from db, pauses execution, freeze the call stock. So it pauses the execution of that function and then freeze the call stock for the other function to use it for them to use the program counter, and then registers continuation. So behind the scenes, first db request sent, non-blocking, and then second node delegates to libhub and OS network. So after the request has been sent, those process or those data is now delegated to libhub and OS for them to receive it once it comes back. Now for Supabase PostgreSQL, what happens? Squill query executed, data retrieved from disk or memory. So it's now in the storage level, query executed, and then data retrieved. Mapping defer, PostgreSQL uses buffer cache, RAM, this storage. So disk to RAM, to query result, to network, and then Node.js. So first, if it's in the RAM, it's in the cache on the OS, it will return that query result. If not, it will check the RAM first. If not, it will check the OS cache. If not, it will check the disk. So the disk is the last phase of querying, and then it will return to network and then Node.js. So back to Node response. When DB returns, callback enters queue. Event loop executes it. So it goes back to the stock, and then the event queue will process it by fetching it to CPU, and then the rest.json parameter user runs. Then back to React, browser receives JSON, then execute. So the browser now receive a JSON. So as you can see, JSON is the format, just like how we discussed in data intensive application. Then set user updates the state and triggers re-render. So re-render call stock, render user profile again. Now where are the fundamentals? Everything you listed appear here. First, memory, stock versus heap. Stock is the function calls. Heap is the object's state closures. So we will study this more deeply in the coming videos. So stock is fast usually for local variables, function calls, etc. used in React State. So the stock versus heap is used, heap object state enclosure, it used in React State, backend objects, and DB results. So those are being used as being stored in heap, in memory data structures. Functions and closures. React component is equal to function. Use effect equal closure over state. Backend handlers equal functions. Event loop and async. Front end, fetch. Back end, DB query. Both rely on event loop, OS input output. Key insight, this is the answer you're looking for. The same fundamental execution model runs your entire app. It's just different layers. So is this the execution flow the same? Yes, at the core, different in structure. Same, stock, heap, event loop, different number of layers, complexity, orchestration. Why these are the real basics? Because no matter what you build, React app, Node backend, database system, they all depend on memory, execution, scheduling. Why revisiting them matters for you specifically. At your level, React plus TS, revisiting this will make async intuitive, eliminate confusion in bugs, help you scale to backend or system design. Final mental model, lock this in. React component to function to stock, state to heap, async to event loop, network to OS, database to memory or disk. One sentence answer. Yes, they are the fundamentals you should revisit because they are the same underlying mechanics powering every layer of your app, from React to Vercel to PostgreSQL. So the core misunderstanding, we fixed this first. You said if prototype is an object, then it must follow a linked list. This is the root confusion. So just because prototype like follow a linked list, kind of like linked list data structure with its pattern, it doesn't mean it actually use linked list under hood. So let's clarify that. You're missing data structure inside an object. So here we're talking about how to actually object are stored in JavaScript. So short answer, by default they are stored in array or contiguous, but for like a more complex or unpredictable object, they are stored in a hash map for them to be able to access in O1 speed. So the relationship between objects, these are completely different things. So a data structure inside an object is actually how those objects stored in memory, or we're talking more like in a Node.js or V8 engine kind of way. But with the relationship between objects or the patterns between your objects in your application with JavaScript, it is more or kind of mimic, but not really the same with linked list. So these are completely different things. What an object really is in memory, forget theory, think like the engine. When you write let obj equal key name with a value John, comma, key age with a value 30 closing, in memory simplified. So this object will be put into heap. So the heap, then object, we have key name, value John, then key age, value 30. Then third is the kind of like heap or is the prototype, and the value is the object.prototype. So the value, the reason why object.prototype is the value is that's how you access that via prototype. It's just like a pattern. It's not really how it is stored under hood. So important, the object is not a linked list, a tree, a single array. It is a dictionary or hash map plus hidden pointer. So what is a hash map here? So instead of name to age to next, it's more like hash name then memers.chan. So it's not contiguous, especially for complex. We will refine this understanding later or in the future videos. But for complex, this is how it works. We use a hash function name and then get its value from the memory. It's not contiguous. Again, hash age and then get its memory. Now engine can jump directly to property. So why not linked list? Because operation like find name, if we do linked list, it has on, hash map o1. Operation JS needs linked list slow, hash map fast. where your linked list idea actually applies. You were very close, just in the wrong place. This is the link structure. So we have object to prototype to null. So this is actually close to a link structure, which is the prototype. So we have the object, it's prototype, and null. Example, object, user.prototype. So we have user.prototype inside the object, and then object.prototype, and then null. So this is a chain of objects, not properties. So inside object, we have hash map. Between objects, it's a pointer chains. So that's different. So inside is the underlying storage structure or in-memory structure with regards to relationship or between objects that pointer chain. So prototype is not a data structure. This is the mental shift. Prototype is now how data is stored. Prototype is how lookup falls back. For example, obj.name, engine does look inside object. Second, not found. Then third, follow prototype. Then fourth, repeat. So this is a lookup chain, not a storage structure. Now garbage collector, this is where people get lost. You said, I only vaguely understand GC. Let's make it concrete. Step 1, everything lives in heap. So when we create let user variable equal an object with a member name value John. So this user is will be put into a stock, so that local variable, and then the reference would be in the heap. Step 2, remove reference. Let's say user is now redefined to null. Now no variable points to object. So step 3, GC runs. Engine asks, can I still reach this object? If no, delete it. If yes, keep it. This is called reachability. Rule, if nothing can reach an object, it dies. Real example, important. Function create user, empty parameter. Inside is let user equal an object with a member name and a value John, closing, then return user, closing, then let u equal create user, empty parameter, then closing. After function, so we have u in a local variable, and then the heap, which is the object name John. So object survives. So after this function, like let's say let u is equals to create user, so that function runs, but still you are the object are still there. The u are still referencing the object, so the u local variable is still referencing the object, so the object survives. But create user with an empty parameter, no reference, unreachable object, so GC deletes it. So this let u is now equal to create user. Since it doesn't have the reference, or it's not pointing to any object in the heap, it will delete it. So 6, how DOM fits into this here big realization. You said HTML becomes objects in memory. Yes, and now we connect it to GC. Example, that btn equal document that get element by ID, parameter string John, closing. Now this btn is a local variable that is now pointing to a heap, which is a DOM button object. Now remove from DOM, btn.remove function, next line btn equals to null. So we redefine the we remove the btn function, and then we redefine the btn equals to null. Now no references, GC cleans it. But if you do btn.event listener, parameter string click, comma, empty parenthesis, arrow function pointing to an empty object, closing. Now event system still references button, object stays alive. This is how memory leaks happen. So if you do this, the btn.event listener parameter click, empty parenthesis, arrow button, you might think you're just writing a code, but you're actually creating a memory leaks, because in the event system now follows still references the button even though it's an empty, so the object stays alive. Connecting to React, this is where it clicks. React constantly creates object, like this object with a member type, value string div, comma, member props with a value another object, then closing. These are React elements or plain JS objects. So these are in the heap. Every render, new objects created, old ones becomes unreachable. So that's the same with React. GC cleans the old ones. React relies on fast allocation plus fast garbage collection. So it relies on fast allocation of the engine and the fast garbage collection as well to be able to make the creation of user app possible, because before it's actually hard to do that in HTML, CSS, and JavaScript, especially before like HTML, CSS, and JavaScript. It's hard to create those application because like an objects make got a lot of memory leaks. So we will discuss that in the future. Basically, our hardware can't process it efficiently, but because of innovation of hardware and software, you were able to now use it conveniently. That's why we were able to work from home. So final unified mental model. This is the truth layer. Objects stored in heap, implemented as hash map, keys to values, and then hidden class optimization. So actually by default it's stored in array. We will refine that. A prototype, a pointer to another object, used for fallback lookup. For forms, chain, not list of properties. Variables, it store primitives, which is the value. And then objects is a reference. So for primitives, it stores the actual value because it's constant. For object, it stores just the reference to the heap. Garbage collector deletes objects when no references exist based on reachability. So if you have no reference, you will delete that object. And DOM, HTML, objects in memory. JS manipulates them. GC cleans unused nodes. For DOM, HTML is actually an objects in memory or it's in a heap, and then the JS manipulates that object in the heap. Then GC still cleans those unused nodes. So those HTML are still being converted into a heap or into a JavaScript object and still being compliant to the V8 runtime engine. So React creates lots of objects, uses reference comparisons, relies on GC heavily. The one sentence that fixes everything: objects store data like a hash map. It's like a hash map because it's fast. But again, by default, it's array. Prototypes form a pointer chain, and garbage collection removes anything that is no longer reachable. So first, values versus reference, the core confusion. This is the foundation. Primitive values, stock-like behavior. So let A equals to 5, closing. Let B equals to 8, closing. Then B equals to 10. What happens? A is equals to 5, then B gets a copy. Why? So we read, 5, we define 5, and then we define B as equals to A. So it's still the same, they have the same like value, 5, and then we redefine B to 10. So A is equals to 5, B gets a copy, right? So A is equals to 5, now we redefine that redefine that to 10, so no connection. Now objects, reference behavior. So this is like a value, a stack like value again. The primitives are in the stack and the objects are, or objects data types are in the reference behavior. So let obj1 equals to member name, value John, and then let obj2 is equals to obj1, obj2 dot name is equals to Alice. So this obj2, since it equals to the John at first and then we rename it Alice, what happens? obj1 and obj2 both point to the same object. So obj1 now is named Alice, and then obj2 is still named Alice. So as you can see, if we do this, like let A is equals to constant, or if we're dealing with primitive data types, it is being copied instead of reference. But if we do this, let obj is equals to an object, and then we like equate that object, those are not being copied, or it's not a duplicated copy like this, like 5 and 5. Here, when we equate this obj2 to obj1, this obj2 is referencing to the same obj1. That's why it's called reference behavior rather than value behavior. So what happens? obj1 and obj2 both point to the same object. So console.log obj1.name is still the same Alice. Key truth: variables don't store objects, they store references addressed to objects. So if you create an object, which of course you're gonna use a variable, they don't store the objects, they store references addressed to objects. So it's the same principle we discussed here. Stock, second, stock versus heap real explanation, not textbook. Stock, fast structured, stores. Function calls, local variables, so that's the variable we're talking about, such as the a or the local. What we mean by local, if it's store a constant value, not dynamic value, such as heap. Function calls, so those again is referencing to a constant rather than dynamic, and then it store references. So function call references, highly related. Heap, big messy, stores objects, arrays, functions. So those are the three types of objects in JavaScript, aside from the 7 primitive types such as string, number. So we have 2 data types in JavaScript, primitives and objects. So these 3 are part of the objects data types. The primitive types is string, number, boolean, undefined, null, big int, symbol. So those are the 7 primitive data types. Now here we have 3 for objects. So heap, it's a big and messy. Let's say function create user empty parameter inside this let user variable is equals to name John. So this again, it's referencing variable referencing to an object, and then return user. So what happens here? The stock, the user is in the stock because it's a local variable, but it's referencing a heap, which is the name John. So important, you cannot see stock versus heap in syntax. JavaScript decides automatically. You also can see that like under hood, the engine will decide under the hood. And also with this like type, though we define this as stock, let user equals to an object, it is actually not being put into a stock because it's within an object. So JavaScript see this this entire function as an object. Therefore, all of these are stored in the heap. So are objects linked list, hash maps, or arrays? You ask a very deep question here. Not a linked list, too slow because it will take an O and look up. So linked list, again, it's just a node that you need to like traverse from the first until the end if you want to get or to retrieve the end value. So you always need to like traverse the first node. That's why it's O and look up. Not purely contiguous because keys can change dynamically. So if you use a linked list, it is not contiguous because the keys can change dynamically. Therefore, reality, so node is non-contiguous, right? A linked list is not contiguous, as we discussed in DSA. So the reality, it's actually a hybrid system. JS engines like V8 use first hidden class, fast path. If objects are predictable, like let A equals to x, member x value 1, then comma member y value 2, then let b is equals to member x value 3, then member y value 4. So engine stores shape x and y. So a is variable is now referencing the value 1 and 2, and then b variable referencing the 3 and 4, and the shape is the x and y. This is array, like contiguous. So these are by default. Okay, so this is the fast path or called hidden class. For hash map, like for example dictionary table, for this simple, this is what I'm talking with simple objects. But for hash map, like dictionary table, if object changes a lot, like obj.z equals to 10, then semicolon, next time delete obj.x, engine switches to key to hash location. So it will hash that key to get that value or that property. Now this is non-contiguous truth. Objects are not one structure, they adapt for performance. That's actually one of the main performance brought by JavaScript that allows it to handle the user application that they are today. So what is garbage collection? GC, you ask, what does garbage collection even mean? Sample idea, the system's frees memory you no longer use. Example, let obj is equals to this object name John. Then you redefine the object equals now to null. Now no references, name is John, GC deletes it. Rule, if nothing points to an object, it gets removed. Real mechanism simplified, mark reachable objects, delete unreachable ones. How OS actually allocates stock and heap. Now we go deeper. When your JS runs, OS creates a process, then the process gets memory, like stock, fixed, small, the next line heap, large, dynamic. So stock OS level managed automatically, grows or shrinks with function calls. Heap OS plus JS engine allocated dynamically, managed by V8 engine, garbage collector. Important, JavaScript does not directly control memory, the engine does. How this connects to React? Now that part you're really trying to understand, React is equals to functions plus objects plus references. So here we have function components, empty parameter. Inside is an object, const parameter state comma set state equal use state parameter count with an initial value 0, then closing. So the state, the stock is the state pointing to a heap. So the heap is the count initial value 0. So when updating, like when a set state count, we turn that into 1. React creates a new object. So old count 0, new is count 1. Why? Because React component references, like all state equal new state is not or is false, so it triggers the render. Prototype in memory, final missing link. So here we have function user, Pascal case again because it's a function, and then empty parameter, and then empty object. Next line, user that prototype that login equals to function empty parenthesis and empty object. Then closing. The next line, const u1 equal new user function closing. So in memory we have u1, we have name colon, and then dot closing, then pointing to a prototype, then user dot prototype, and then that user dot prototype pointing to right arrow log in with the value function. The key inside function exists once in heap. All objects points to it. Event loop plus OS plus browser full flow. Let's connect everything step by step, real world. First, you open a website. OS creates browser process. Second, browser loads JS. JS engine parses code. Allocate memory, heap plus stock. Third, event loop starts, call stock, then event loop, then callback queue. So this call stock and then callback queue. This callback queue is for like the outside or asynchronous operation. Example, set timeout. Arrow function console.log parameter high comma 1000. So flow, set timeout. It calls web API browser for it to be able to wait for that 1000, and then timeout second, timeout runs outside JS because that's from outside or web API. Third, callback goes to queue, it goes back to the queue, and then fourth, event loop pushes to the stock, and then it executes. So after this timer, that's the time it executes. Key inside, JS is single threaded, but browser plus OS are not. 9, connect everything. This is the click moment. Here's the full system. Your React code to JavaScript to JS engine V8. So that JS engine was allocated the stock heap, and then it has additional garbage collector aside from the stock heap provided by the OS. Now this JS engine, so it has an access to browser API, which has an access on OS memory plus scheduling. So we discuss in OS that an OS has stock and heap, and that it has a code. It compiles that code first before it provides the stock and heap based on the code program, right? So this is different from that because it has this intermediary of browser along the way, unlike with the normal process in a desktop or laptop application. CPU executes and then OS memory scheduling, then CPU executes instruction. Final mental model, very important. Forget all confusion. Keep this. Variables hold values or references. Second, objects lives in heap. Third, stock trunks execution. So its stock is the same of the program counter in CPU architecture we discussed. Fourth, prototype shared behavior via pointer chain. Fifth, GC remove unused objects. 6, React compares references to detect changes. Event loop. 7, event loop um, schedules execution. The real core truth, JavaScript is a system of references, dynamic objects, shared behavior, prototypes, automatic memory management, not strict memory control, fixed data structures.